Thanks to Professor Marcello Massimini, full professor of physiology at the Department of Clinical and Biomedical Sciences at the University of Milan, Italy. Thanks for connecting to this short interview about your seminal plan for Sapienza Neuroscience on February 26 this year. And you are really well known for your exciting scientific studies on human consciousness. And is it possible today to localize the function of consciousness in some place in the brain?
Thank you, Claudio. This is obviously a relevant question. And it's very interesting, by the way. So, first of all, there is an interesting question, which becomes even before that, is what kind of neuronal processes are relevant for consciousness. And I think, in general, the community over the last years has been sort of converging on some processes. So there is, if you review the literature, there is an interesting growth of paper showing that measure of dynamical complexity or complexity in the brain are those measures that better reflect the level of consciousness, at least. So this seems to be an interesting process. Where is this happening? So whether there are parts of the brain that are very relevant and others that are not relevant is the next question, and it's a great question. So for example, taking an extreme example, the cerebellum, it's huge in terms of numbers of neurons. It's a small structure, but it's huge. It has most of our neurons, basically, and it's well organized with a lot of inputs, outputs. The problem with the cerebellum with respect to consciousness is that we can remove it and nothing changes. And we think we know why, because the cerebellum is a modular structure, and as such, it is not capable of generating complex patterns of interaction because of its modularity. So this is already an interesting aspect. Whether differences are present within the thalamocortical system, where some areas are more important than the other, it's really a current debate, and it's an interesting debate. So there might be some areas that, like the cerebellum, are less important and less well suited to generating complexity. So in general, in the science of consciousness, there's been a lot of emphasis on the frontal lobe, historically, for historical reasons. It's the last part of the brain that evolved. It's very important for our behavior. It's what makes us human in some respect. And also experimental designs were made in a way that basically favored the frontal lobe, because the typical conscious experiment is that subjects are looking at the image. The image is not very clear, and you have to press a button when you consciously perceive the image to detect the neural correlate of consciousness with fMRI, EEG. And when you do this kind of experiment, you always see that when you become conscious, you have a strong frontal activation. And thus, researchers said, well, the frontal lobe is where everything happens. But in reality, recent research shows that this activation is more a correlate. It's not a correlate of becoming conscious. You see the image, but you have that activation because you are deciding to press a button. So you have that as, let's say, sort of an artifact or a correlate that you are doing something about being conscious. So if you do the same experiment and subjects are seeing the image, clearly seeing the image, but they are not asked to report, you see that the activity is more towards the back of the brain. So this is a new line of research which will require new experiments, and there are a lot of labs doing this kind of experiments in no report condition to disentangle what is a correlate of pure consciousness and perception as opposed to a correlate of reporting, working memory, and all these functions that builds on top of consciousness. And it's definitely a very interesting research because it also has to do with the definition that we give of consciousness. If you give a definition of consciousness, it's mainly an executive thing, and you judge consciousness by behavior, you're going to find the frontal lobe every time. But if you think about consciousness as perception, presence, being there without doing much, then it's more the parietal and the occipital lobe that matters. So we also have to decide what kind of definition we want to adopt and what we are interested in. Otherwise, it's a little bit like confusing being with doing. And it's obviously it's a very important thing that we need to decide, but we'll see interesting things in the years to come.
Okay, it's very clear that consciousness is maybe related to several processes in the brain, and so several circuits and so on. Thanks for this clarification. And we know that some brain diseases are related to loss of consciousness in humans. And can science predict if patients with this loss of consciousness, such as coma or persistent vegetative state, for example, the kind of brain disorder of Michael Schumacher, the former Formula One driver, can science predict the recovery of consciousness in these patients today?
Yeah, there are good clinical markers, but it's not enough. So science has a role to play here. And so there are two problems here. The first problem is deciding whether a subject is already conscious, but you don't see that through behavior. So this is you can call it a diagnostic problem if you want, because you want to know if the subject is conscious there and now, although it's fully paralyzed. But in a way, it has a prognostic flavor, because if the patient is conscious but unable to show, it is likely that sooner or later it will show that. So it's more like a short-term, either a diagnostic problem or a short-term prognostic problem. Here, also, as I said before, the community has been developing interesting markers. Really, this has been happening in the last 5-10 years, and we have good brain-based markers that are either derived from fMRI or EEG, and they are all looking basically at the same thing: the ability of the brain to support network that are sort of large scale, integrated, of interacting element, but also dynamically rich. And we can look at this with fMRI, with EEG, with TMS-EEG, and many different techniques. If you see that in a patient, even though the patient is not behaving, is not responding, is in a coma or in a vegetative state, if you see this kind of process building up in the brain, this is a sign that the subject is either conscious but disconnected, or that he will recover shortly after. So this is kind of emerging as a consensus. About the long term, and you mentioned Michael Schumacher outcome, of course, there are basic clinical indicators. I mean, a traumatic brain injury is likely to be, to recover more likely than a post-anoxic, cardiac arrest brain injury. But this is very general. It's on average. And when it comes to individual subjects, the long-term prediction becomes very, very difficult, because many factors come into play. And also you could have cases in which the brain is okay, the lesion is not so big, but it's in a critical spot that is blocking the reemergence of complex dynamics, let's say. So it looks good, the brain is okay, but it's not starting. And the problem there is, of course, guessing whether it will start or not, it's difficult. There are rare cases of patients who recovered after 10 years. But most important, it's key to understand the physiology, the underlying physiology, in order to be able to understand whether and how we can restart it when it's stuck in some, configurations that are not compatible with consciousness. So that's a great big challenge, and I think it's where we have to devote a lot of attention in the field.
Thanks a lot for this clarification about the advances in the field of clinical applications of your science. And I am very curious to follow your seminar on February 26th this year, and we will launch your the date and the link to be connected to your seminar. So thanks a lot again. Bye-bye, and see you for your seminar.
Thank you, Claudio. Looking forward to it, and I'm very excited. Thanks a lot for the invitation, for the questions.